Okay, here we are in the last part of the first lecture about ordinary differential equations. So the last piece is about the first order linear ODEs, which are maybe the easiest case. Okay, so we want to solve this equation where we have only u and its first derivative. That's why we have first order. And we are still a linear ODE because we have here a coefficient and here there is a 1. And we have this function g here. Okay. This is not necessarily a number, it's a function, and same for g. So we want to solve this equation. The trick here is that we will use an auxiliary function. You look this small p. We will consider capital P an antiderivative of a small p. That means that when we differentiate p, capital P, we recover small p. And we multiply the equation by this exponential to the power p, capital P, the function. Okay, so we start with our first linear equation. We multiply for this auxiliary function, both sides obviously to keep the identity. Then we distribute this and we get this other expression here. And now here, by the chain rule, we know that this is exactly the exponential capital P derivative, the first derivative of that. So we can rewrite the equation in this way. And now if we pay attention to the whole side of the equation, by the product rule, we have exactly like the first derivative, the second no, and the second derivative and the first no. So we have the product rule here. That's what I meant. So we have exactly this expression. And now it's easy because we can integrate and get, okay, this original function, let's say, and we have a constant that comes from the integration process. Here is a constant, it's a number. And okay, we have the integral here in this side of the identity. Okay, so now we realize, and we were using that a lot, that the exponential to the power something, whatever, is never equal to 0. So we can divide by it. Dividing, so this exponential goes to this side of the identity, we get exactly the solution u. So if we now remember the variable x, because here we were omitting the variable x, so we can write these calculations like easily. But now if we remember that we have the variable x, this is what we get as a solution. And you can use this as a result in all the exercises that involve first order linear ODE with these two guys, p and g, not necessarily numbers, just functions. Okay, so the general solutions to this first order linear ODE has this form. E minus capital Px times this constant c that we have no idea, it's just a number, and the integral of e to the power capital Px times g. And this capital P, remember that this is an antiderivative of p, small p, where p is this coefficient of the equation. Okay, so now imagine that apart from the equation, we have initial condition. As I said in the previous part of the lecture, usually a first linear equation has one initial condition, a second one has 2 initial conditions, a third one 3 initial conditions, and so on and so on. So now if we have this initial value problem, we know the general solution of this part of the equation is given here, this blue expression. And what we don't know here is this constant c. So with this initial condition, we will determine this constant c. That's the idea. So let's try to fix what we just saw with this example. We want to solve this initial value problem. We have this first linear ODE and with this initial condition. So to find the general solution of the ODE, the ingredients are, we have to know who is P and who is G, and once we have that, the only ingredient that we need is capital P, which is an antiderivative of little p, because that's what we saw here. If you want a solution of this type of equation, you just need to identify who is P, who is G, and once you have that, you find an antiderivative of P, and then you write this and you get your solution. So that's what we are going to do. We identify who is P and who is G in this example. So P is hidden here, is equal to -1. So an antiderivative of P is capital P equal -x, because when we differentiate it, we recover the -1. And G is equal to 2. So now we use the expression. We know that the general solution U has this form, where C we have no idea, it's just a constant. So minus capital P, here in our example, that is just x here. The constant stays the same. Capital Px is E minus x, which is here, and G is 2, which is there. So that's why I said replacing our information in the general solution, we get, after some computation, this U, Cex minus 2. So finally, this constant C that we don't know so far, the value, we determine this constant with the initial condition that we have, which is U at 0 is equal to 3. So we go and replace this information here in our function, which means that C, this constant, is equal to 5, sorry. So finally the solution of this first order linear ODE is phi Ex minus 2. Okay, so that's it for now, for today. So you can read the textbook, the appendix A1 and A2, and some exercises are here. Maybe this information will be also in Blackboard, so you don't have to read this now. So good luck with the content of this lecture, and see you next time.